This lesson is about related rates. So let's talk about what that means, related rates. Let's look at this balloon, for example, and pretend that it's not blown up yet. Let's just say you're going to blow this balloon up to make it bigger. So if we just blow up the balloon and make it larger. Let's just talk about the balloon itself. Let's not talk about the string. So what happens, what's changing as the balloon gets blown up? So there are many, many things going on here. And as time goes by, the more you blow the balloon up, the more things are changing. So I want you to take a moment and think about all of the things that actually change on this balloon as you blow the balloon up. Okay, so let's talk about that. As you blow the balloon up, first of all, the radius increases. Would you agree? As the balloon gets larger, the radius gets larger. So we're going to use, and this is as time goes by, because time is what we're measuring things in. As time goes by, the radius gets larger and larger. So the variable we use for that is dr dt. It's the change in radius over time. Specifically, it's the change in radius as time changes. Okay, I'd like you to think about other things that are changing here, and what variable could you use for those changing parts of this balloon, or components of this balloon. Take a moment, write out a list of as many things as you can think about that are changing, and see if you can come up with a variable for each. Okay, welcome back. I hope you actually did that. Well, if the radius is changing, I know that the diameter is also changing. So it kind of seems weird, but I'm going to use dd over dt, change in the diameter as time changes. I know that the volume is also changing. The amount of air inside of the balloon is changing. That's the change in the volume. I'm going to use dv dt. That's the change in volume as the time changes. And the surface area of the balloon is changing as well. I'll use A for surface area. That's the change in the surface area. You may have thought of some other interesting things that change as well, but for now that gets the point that I'm trying to get across. When we talk about related rates, we're talking about so many moving parts going on at the same time. So as time is going by, all of these things are changing at the same time. They're not all changing at the same rate. The radius and the diameter will change differently than the volume is changing, and will change differently than the surface area. So what we're going to do is try to come up with a way to relate these rates together to learn more about them and how they're changing as time goes by. So let's do an example. We'll do just two kind of not too difficult, kind of straightforward questions. Let's do this one. We'll just do this together, and I'll walk you through it. The first one is, how is the area of a circle changing when its radius, I should have had these written out before, sorry. When its radius, I will in the next video, is changing at a rate of 2 millimeters per second when the radius is 5 millimeters. Okay, so we're going to look at a single moment in time. So So the circle is changing as the radius is changing. So let's take a look at this. When you solve a related rates problem like this, there are certain steps I like to follow, and I recommend you follow those same steps. So for example, in this case, in every case, I'm going to start by drawing a picture. So this is a circle. Thank you, Notability, for making an actual circle. So that's the first thing I do, is draw the circle, draw the picture, and put in the information I know. So right now, what I know is that the radius is currently at 5 millimeters. So the radius is currently at 5 millimeters. That's the moment of time we're concerned about. They told us that the radius is changing at a rate of 2 millimeters per second. So what would the variable be for the changing rate? Notice that it's millimeters per second. I hope you were thinking dr dt, changing radius as time is changing. So where the radius is changing at 2 millimeters for every second that goes by. So the radius is getting larger. The question said, how is the area of a circle changing? So what we're looking for is how the area is changing. Okay, so step one, when I'm solving a related rates problem, step one, draw a picture. In this case, our picture wasn't very interesting, but believe me, it gets way more interesting later on. Second step, define my variables. The third step is the most crucial. The third step is to find an equation that relates all of these variables together. So since we're talking about the area of the circle, and we're trying to find how area is changing, I'm going to use the equation for the area of a circle. Okay, step one, draw the picture. Step two, define your variables. Step three, find an equation that relates those variables together. Step four then is to differentiate that equation. Because if we differentiate that equation, that'll talk to us about rates and will help us find how things are changing as time goes by. So for step four, to find the derivative, notice that everything is with respect to time. This is as time goes by. So we're going to differentiate this area equation with respect to time. Give it a shot. We practiced this before. So try it here in this situation. Pause the video. See if you can try. Okay, welcome back. I hope you tried. We're going to use the chain rule. In this first situation, we have the derivative of a, the derivative of the area with respect to time. There is no inner outer function because it's just straight up a. There's no outer function, it's not a cubed. So the derivative of a is just dA dt. The area is changing as time is changing. On the right-hand side, we don't have a product rule here because remember, pi is just a constant. R, however, we get to use the chain rule on R because we have an outer function and an inner function. The squared is the outer function, the R is the inner function. Okay, so we're going to use the chain rule. I'm going to bring the 2 out in front, so that makes this 2 pi. Don't change the inner function, so leave it as R. And then multiply by the derivative of the inner function. And the derivative of R is dr dt. Okay, finally, our last step in related rates problems is to use that rate equation we came up with and substitute in the values we know, solve for what we're looking for. So in this case, we're trying to solve for dA dt, and we know all of these other values. So dA dt we don't know. That's what we're looking for. We know R in this instance is 5, and we know dr dt is 2 millimeters per second. So if I replace all of this, it's 2 pi, the radius is 5, dr dt is 2. So the area is changing. 2 times 5 is 10, 10 times 2 is 20, 20 times pi. 20 pi is how the area is changing. Now here comes the kicker, what are the units? We actually have a real problem here. This is based off some real work. So we need to have some units to go along with this so that this will make sense. We're talking about the area of a circle. So if you were finding the area of a circle, think about what the units would be. Since we're working with millimeters and we're working with area, this would be millimeters squared per second. Area is measured in millimeters square and time is measured in seconds. So that's really important when you come up with a final answer in a related rates problem, that you have units that make sense. Okay, that's the first one. Let's try another one. I'm gonna go with red as my main color and then highlight with blue, just to mix it up a little. The water level of a conical tank. That means a tank shaped like a cone is rising at a rate of 0.2 feet per minute. If the radius is changing at a rate of 0.1, sorry, I really should have had these written out. Feel free to skip along. Oh geez. 0.1 feet per minute. Sorry about that one. What is the rate of change in volume? When the radius is 1 foot. And the height is 2 feet. Okay, I want you to pause and I want you to try to do as many steps as you can. Step 1, draw the figure. Step 2, define your variables. Step 3, find an equation that relates all of those variables. Step 4, differentiate that equation. And then step 5, plug stuff in and solve for the variable you're looking for. Come back here once you've attempted it. Okay, I hope you gave it an attempt. We have a conical tank, so you can think about this tank either way. I'm going to think about my tank as being flat on the bottom with the point upwards. So the tank is shaped like a cone, and there's water in the tank. I'm going to get really specific here with my drawing. Here's some water in the bottom of my tank. Okay, right now there's some information I know. I know that the rate at which the water is rising is 0.2 feet per minute. So that means my height is changing. dH dt is increasing at 0.2 feet per minute. I also know that the radius of the water is changing. So if you think about this, there's another circle at the top of the water. I also know that the radius is increasing. So dr dt is also increasing. Oh, which means this cone's turned upside down. Darn it. Sorry. Let's make this more realistic, because if the way I drew it, this cone were in this direction, the radius was actually getting smaller. So really what's happening is this tank is upside down, which means my water is at the bottom and filling up. It kind of makes more sense. Easier to put water in there if it's in this shape. So the radius is increasing. So now it makes more sense. All right, let's try this again. So dh dt is 0.2 feet per minute. The radius is increasing. So dr dt is 0.1 feet per minute. What is the rate of change in volume? So what we're looking for then is dv dt is what we're wondering about when the radius is 1 foot. So at this moment in time, r equals 1. And at this moment in time, the height equals 2. Wow, there's a lot going on here. A lot of moving parts. So we have the image. We have all of our variables defined. Now we need an equation to relate these variables together. Since we're looking for the volume of water in a cone, we need to know the volume of a cone. So the volume of a cone is pi 1/3, wow, 1/3 times pi times the radius squared times the height. Do you need to know that? Most of the time, no, but sometimes yes. They'll expect you to know some of the common volume formulas, so it's best to just know it. But sometimes they'll give it to you, and then it's a happy thing. All right, here comes the interesting part. Now we're on step 4, where we find the derivative of this volume equation. We have 2 different variables we're looking for in this case. We've got radius and we have height. We actually have 3 because of volume. So that means on this right-hand side, we need to use the product rule. On the left-hand side, that's just volume, so we'll be able to find the derivative of volume, and that is dv dt. I'm going to count 1/3 pi r squared as g of x, and I'm going to count h as h of x. So in order to use the product rule then, I need to find the derivative of g. The derivative of g, I'm going to use the chain rule. So I'm going to multiply the 2 out in front, which is 2/3 pi without changing the radius or changing the inner function, multiplied by the derivative of the inner function. So I just used the chain rule on r squared. Now I'm going to multiply by h because I'm in the middle of the product rule still, plus g of x unchanged times the derivative of h with respect to time is dh dt. Okay, finally for my last step, I'm going to plug things in. I'm looking for dv dt. I'm going to replace everything I know. The radius in this moment in time is 1. I know dr dt is 0.1. I know the height is 2. 1 squared. And dh dt is 0.2. Without a calculator, you should be able to do this without a calculator. So I have 2/3 pi, I'll just leave that there for now. I know that 0.1 is 1/10. So if I multiply 1 times 1/10 times 2, that's 2/10, or 1/5. So this becomes 2/15 pi. All right, on this next one, 1 squared is 1. 0.2 is 2/10, or 1/5. 1/5 times 1/3 is 1/15 times pi. If I add 2/15 pi plus 1/15 pi, that's 3/15 pi, which reduces to 1/5 pi, or pi over 5. Wow, that's dv dt. That's the rate at which the volume is changing. Volume now. So what are the units for this? The units in this case, since we're talking about volume, are feet cubed per minute. That's the rate at which the volume is changing at this instance, at this moment in time. Okay, the next video is going to use some slightly more advanced techniques, so I'll see you there.